Thank you everyone for joining. This is Momo. As Sophie said, I'm a researcher in Artinis, and my main job is about the estimation of physiological noise. So as the model of the company is to make optical brain imaging easy, I was hired to extract extra physiological noise and implement them in our software. So that's why we have this talk today. So firstly, I will give you a really short introduction about fNIRS, what it is, why we do that in general. And then I talk about really briefly about the background of physiological noise in fNIRS. Then we go to the research question and goal. And afterwards, I talk a little bit more detail about cardiac pulsation and respiratory effect on NIRS data and how we can estimate them. And I finish my talk with a few conclusions. Okay, so what is fNIRS? I'm pretty sure that most of you already know that, but just in case. Well, fNIRS stands for Functional Near Infrared Spectroscopy, which is a non-invasive optical brain imaging techniques. The reason we use that is to monitor or to get brain activation in response to its stimulus. And what it measures, obviously, it's changes in hemoglobin concentration. Specifically, we are looking for oxygenated and deoxygenated hemoglobin, which we know them as O2HP and HHP. So what eventually we expect to receive from fNIRS is called hemodynamic response function. So this is exactly the brain activation we're looking for. The motivation behind it is pretty simple. So when neurons become active by a stimulus, they consume more oxygen, leading to an increase in O2HP cycle. And when a decrease, of course, in the deoxygenated hemoglobin, this is called HRF. And the shape and timing of HRF is really important for researchers, for us. And we usually do that for our analysis. So as example, in the graph on the left side of the screen, you can see for from second 0 to 5, we give a stimulus. So we had increase in oxygenated and decrease in deoxygenated hemoglobin. And after a while, after the stimulus is done, both measures are going back to their baseline. So the basic of NIRS is pretty simple. We shine near infrared light into scalp by transmitter and measure the amount of light that is either absorbed or scattered by trained tissue using receivers. So in this graph, you can see we have one transmitter, we have one receiver, and we place them with a distance of 3 centimeters from each other. And using transmitter, we scatter light, we shine the light, and those lights, they have wavelengths that are in the range of oxygenated and deoxygenated hemoglobin. So based on that, we can measure fNIRS data. I'm afraid the output of NIRS is not simply HRF. In order to get that, you need to do some work. So here's an example. It's 30 seconds of the recorded fNIRS data during the stimulus, and you can see from second 10 to 20, we don't have a clear HRF. The reason for that is fNIRS data is contaminated by systematic physiological noise, which are quite strong compared to HRF you're looking. So in order to get a good HRF, you have to remove those components. So I'm not going to really go into details about HRF and how we can extract it. We have some materials in our YouTube channel you can watch, or I think within 2 weeks, we're going to have an on-site seminar about introduction about fNIRS, where my colleagues are going to explain to you in details that how we can extract HRF. So here I'm just going to talk about physiological component, but if you need more information, please visit our YouTube channel or just contact my colleagues for further information. So on the right side of the screen, you can see a spectrum, or FFT, let's say. This, I think, easier term. A spectrum of fNIRS data. So as you can see, we have several peaks in specific frequencies, which each of them stands for something. We have Mayer waves, breathing rate, and heart rate. The first good thing about fNIRS compared to other brain imaging modalities is the lower vulnerability to subject movement and electrical noise, for example, compared to EEG. But it is strongly contaminated by systematic physiological noise that have to be removed in order to have a good HRF. However, those physiological noise might be helpful for some reason. So first, let's give a little bit of explanation about why we have this physiological noise, and then I will talk more detail what we can do with them. So the first one is cardiac pulsation. So as blood pulsates through the vasculature, it causes fluctuation in the amount of the light that is absorbed or scattered by the tissue, which leads to this variation in fNIRS data. So as you can see, it's oxygenated and deoxygenated signal. In both signals, we have somehow a periodic cycles, where in oxygenated it's a little bit stronger, not a little bit, quite stronger compared to deoxygenated. And each cycle here stands for one cardiac cycle. So cardiac cycle or cardiac pulsation is the strongest physiological noise we have in fNIRS. Second one is respiratory effect. Well, obviously, when we inhale and exhale, it leads to changes in volume and oxygenated level of the blood in the cerebral vasculature, which affects, again, the light absorption property of the tissue and results in some sort of a fluctuation in fNIRS measurement. However, compared to, obviously, heart rate, it's going to be slower fluctuations, but they're there. So you have to deal with also with respiration noise. Lastly, we have Meyer waves. So we can say like somehow they are due to changes in blood pressure. Well, changes in blood pressure can lead to alternation of cerebral blood volume and volume, which of course impact the properties of the tissue and leads to somehow variation in our data we are not looking for. And the reason for that is, changing blood pressure can also change the vascular tune, which can affect the signal here. So here's also, you can see oxygenated and deoxygenated hemoglobin data. But compared to respiration, heart, cardiac pulsation, you can see here they are quite slow. So for example, you could see them in like 100 seconds or 50 seconds. But this is also one of the physiological noise that you have to take care of them when you're doing your analysis. Okay. So let's talk about the fact. If we want to get the HRF, as already said, we have to filter those physiological components out of the data. However, they hold valuable information for us. So, for example, we conducted a study about mental workload assessment. On that study, we showed that if you combine brain activation and combine it with features that are extracted from a spectrum of the NIRS, where respiration and cardiac activity exist there, you can improve the data analysis. Because eventually what you're looking for is to, for example, do a better analysis for mental workload assessment or something like that, right? So if you have one signal and you can extract further information, well, you should do that. It's a free tool for you. So the question is, can we take advantage of such vulnerability of the fNIRS data to this systematic physiological noise to extract complementary information where we can use them alongside the brain activation? So yeah, that's the answer is yes. So that's why we're going to talk about potential methodology that we can use to obtain this extra information, just which can be used alongside the HRF and improve our final assessment. So the first one, as I already mentioned, cardiac pulsation is the prominent physiological component present in NIRS. This is the strongest. And actually, cardiac rhythmic activity in NIRS is shaping the signal profile. So based on that, we can use it for somehow, we can use this vulnerability for data quality assessment, which is really important when we are doing fNIRS data analysis, because we wanted to make sure data quality is good so we don't get false positive. Right, so based on that, we could say strong cardiac component indicates good quality of fNIRS data, which reflects good upload-scalp coupling. So here you can see two graphs here. On the right side, we have a good quality data, not good, great, I'd say. And in the left side, we have really good quality data, and in the right side, we have a quite bad quality data. So as already explained, both for optical densities and for oxygenated and deoxygenated, we have a strong cardiac component. But on the right side, we have something which is quite random, I'd say. So based on this property, in our company, we develop an algorithm which is called Signal Quality Index that is aimed to score the quality of 10 seconds fNIRS data from 1 to 5, where 1 stands for lowest and 5 stands for the highest. So our algorithm consists of 4 stages. First, we do a little bit of pre-processing to remove unwanted interfaces. In the second stage, we identify very low quality signals. In the third stage, we identify very high quality data. And in the last stage, we do signal rating. So each stage, I'm going to explain it to you in detail a little bit. So first part is pre-processing. So of course, what we are recording with NIRS is going to be optical density. We have to convert it to oxygenated and deoxygenated hemoglobin concentration. So for that, we Beer-Lamont law. Then we trend the data, both ODs and hemoglobin concentrations, because we don't need that. And then we do a little bit of bandpass filtering from 0.4 to 3 Hz, also to remove unnecessary component that we are not looking for. To have so all we're doing here is to make sure that we're going to have a clear cardiac components. So the first stage is going to be identifying very low quality data. So the first criteria for us is amount of light that is observed. We don't want too much light. We don't want really too less light. So based on that, we can define thresholds of the OD values that if we have any values which is below or above our linear range, so we just say, well, that's not a good data quality. So the second one is to look for flat lines. So it's very simple. If you have optical density or NIRS data in general that is 0, it's nothing. So on that case, you're not going to have a good data because you recorded nothing. And the second criteria is to check the STD of optical densities per wavelengths. And if either of them are 0, well, on that case, we're going to get SQI of 1, really low quality. So the third one is the ratio of O2HP to HHP summation. So what we also, something else I like to mention here, cardiac pulsation is very stronger in O2HP compared to HHP. So if we use that, and if we have a condition where the amplitude of cardiac pulsation in HHP is stronger than O2HP, but also that's going to be something wrong there. So that's also another criteria we're using for the data quality assessment for really low data quality. So if either of these situations are true, then we consider our SQI as 1. In the second stage, we're looking for really high quality data. So the feature we're using here is a standard deviation of the difference between optical density signals autocorrelation. So for very high quality data, autocorrelation of 2 optical densities should have similar amplitude and shape. And so if they are in this situation, the standard deviation we expect it to be very low. So based on that, we have defined a threshold which works based on this difference. So if, for example, let's say we put threshold at 0.1. So if threshold is met, on that case, the data quality is quite high. So this is one example I put there here for you. So you can see on the right side, we have autocorrelation and they are quite similar. So that's also good quality data. Sorry for that. So in the last stage of SQI, we just nor we have really low quality data, neither we have really high quality data. So for that reason, we can use logarithmic of the ratio between a standard deviation of O2HP and HHP. So as I said, in high quality fNIRS data, magnitude of heartbeat in O2HP signal is stronger than HHP. Therefore, we can expect that the standard deviation of O2HP also be higher than HHP. So based on that, we have this formula as a third feature, which is used for rating the data when neither we have low quality nor we have like very high quality data. So to test our algorithm and tune our parameters, the threshold I mentioned, we use two databases. We use one database for tuning the parameters and the other database for testing. So the second database was completely unseen. We just wanted to make sure that the parameters we tuned, they work perfectly well. So for that reason, we also ask our experts, 7 experts, to rate the data we recorded. And based on that, we also compare the performance of our algorithm with 2 more, FOBI and SCI. And as you can see in the table, we worked way better compared to them. However, it should be also noted that those algorithms there, the FOBI and SCI, they are binary, so they are either good data or bad data. But what we did with the SQI to give a range to our customers, because in some cases, even like medium quality data should be usable. Down there also is a link to our paper and the code, so they are freely available. Even if you're not our customer, you can use them. You can use this algorithm. And for more information, of course, read the paper. This detailed information can be found there. So the second application of cardiac pulsation can be heart rate estimation. So first of all, heart rate is the number of heartbeats per minute, which is measured via electrocardiogram or ECG. So in this case, you can see for 5 seconds, we have 5 cardiac cycles. So the heartbeat is 60 beats per minute. Why it's important? Because it's a really fabulous indicator, which can be used for assessing stress, fitness level, mental workload, and these sort of stuff. So there's a wide range of applications where you can use heart rate changes as a complementary information alongside the brain activation. So fNIRS, as I said, it's the strongest physiological noise. So we can easily use oxygenated hemoglobin, oxy data to estimate heart rate. So the first method we can use is simply to detect peaks. So as you can see, for ECG, we have 5 cardiac cycles. Also for oxy and deoxy data, we have 5 cycles. So if we can detect peaks, then the maximum of each cycle, we can use the number. For example, 5 seconds, we have 5 peaks. So 5 divided by 5 multiplied by 60 is going to be our heart rate. Right now it's 60. And you can see for both ECG and NIRS data, we have 5 peaks, which, well, it's the same estimation. In order to do that, you can use either AMPD algorithm, which was designed actually for detecting peaks in noisy periodic or semi-periodic data. So that's the link to the paper, so you can use that. It's a really famous algorithm. Or if you're a MATLAB user, well, of course, you can use findpeaks, which should require you to adjust a little bit of parameters, but also that's going to be a really nice function that you can use for HR estimation. Well, the second method you can use is autocorrelation. So autocorrelation calculates signal similarity with its delay version, right? So we can expect that first local maxima after the highest peak, which means lag of 0, suggests how periodic the signal is, or let's say it suggests periodicity. So given that cardiac cycle in O2HP or optical densities are super clear and they're somehow periodic, so we can use autocorrelation to estimate HR as the lag value of the yellow dot here multiplied by 60. So you can see in lag, when lag is 0 at first local maxima after that can indicate the heart rate. So we can use that method, autocorrelation, for estimation of heart rate, which is also the case here. We have 5 cardiac cycles in 5 seconds. So the heart rate is 60 beats per minute. And now we have it 1. So if you multiply 1 by 60, it's going to be 60 breaths per minute. So the last method, which somehow I believe it's the most straightforward strategy that you can use for heart rate estimation, is the spectrum analysis. So for that, when we have the periodic signal, we believe that it repeats itself over time. So therefore, if we extract it, if we get it spectrum, we can obviously see a distinct peak at the dominant frequency. So for that, also for HHP, for O2HP, I'm sorry, and ODs, because we know we have somehow a periodic cardiac cycles. So we can use a spectrum of the O2HP or OD values, find the dominant frequency, and multiply it by 60 to get the value. Here's the example. First method, most straightforward, is use FFT, fast Fourier transfer. So in this spectrum, you find the dominant frequency, which is around 1, and you multiply by 60. Another method you can use is also prediogram, and or another, I don't know, another spectrum analysis called Welch. So if you use, you can also use Hilbert transfer or something like that. So spectrum analysis in general is really straightforward. And if you have a clear data, you have a really high chance that you could estimate HR with really low error compared to the reference data. So to test what we have done, we recorded the database. We asked our subjects to do biking for almost 16 minutes. At each biking block, a subject biked for 8 minutes, wherein every minute the resistance of the ergometer increased by 1. And after 8 minutes, we have 1 minute of rest. So this way we expected to generate a really dynamic heart rate, so not just having that in rest. So this way, with this data recording, we increase the resistance. So this way, the heart rate we expected to be increased. So here you can see the result. I just plotted the heart rate as a function of the time. So we have the reference heart rate, which was extracted from ECG, the blue line, and we have estimated heart rate using FFT, peak detection, and autocorrelation. So as you can see, for all cases, they are quite similar. There is no like a huge difference between different methods. And well, here, this is what we expected. We expected to get such a waveform, because at the beginning, by each minute, the resistance increased, so the subject need to the subject heart rate increased somehow. And for all these measures we have used here, the mean absolute error between reference HR and estimated HR by NIRS was smaller than 1 bit per minute. So it's a quite accurate estimation. So about the second topic, it's going to be respiratory rate estimation. So respiration is one of the main physiological noise in NIRS, which manifests itself in a spectrum of the data from 0.1 to 0.4. Well, respiration also has blood pressure and CTO level, which impacts the cerebral blood flow. This effect is expected to be more pronounced in O2HP than HHP, because O2HP is closer, has a closer association with cerebral blood flow. So the strategy that you can use, first you can use a really simple bandpass filter, for example, from 0.1 to 0.4. The second strategy is to do spectrum, because we already know the spectrum we're looking for, 0.1 to 0.4. And the third one is based on doing some modulation. So the first method is quite simple, but also it's not really well, great. in terms of accuracy, because it's not clear from 0.4 to 0. For example, 0.1 to 0.4, or it should be from 0.1 to 0.6, because it really depends on the subject, and it depends if you're resting, you're cycling or something. The second one also about the spectrum analysis, we have two peaks in 0.2 and 0.4. So again, it's not clear which one is the respiratory rate, because the difference of them is about 100%. There is difference if you multiply by 60. So this is also another problem of the spectrum. So the safest option that is also suggested in literature is to do modulation. So I'm going to just explain how we are doing the modulation for different data. So the first modulation we have, we call it frequency modulation. So when we are inhaling, our heart rate increases, and when you're exhaling, our heart rate decreases. So each cycle of, and given the fact that each cycle of the O2HB data is heartbeat, so respiration can cause frequency modulation in our oxygenated data. So here you can see the example that during inhalation, heart rate is increasing, and during exhalation, heart rate is decreasing. So the distance between two peaks of the cardiac cycles can be a good indicator for us. Well, the second modulation is amplitude modulation. So when we are inhaling, thoracic cavity expands, which leads to venous return to heart increases, and as a consequence, higher blood volume in the cerebral vasculature would go. Well, this is the opposite for exhaling. The thoracic cavity contracts, venous return to heart decreases, therefore lower blood volume in the cerebral vasculature can be expected. So you can see here this fluctuation in blood volume induces amplitude changes in O2HB signal. Sorry for that. So these differences between those troughs and peaks, those blue dots and black lights, they can be used to generate a modulation, amplitude modulation, for estimation of respiratory rate. So lastly, we have intensity modulation. So when we are breathing, well, it involves movement of the thoracic cavity, which can cause mechanical changes in blood vessels and tissue, which are near the fNIRS optoids we have. So these changes can be, mechanical changes can show itself as a smooth changes in the baseline of the data, as you can see, and we can also use that for estimation of respiration from the NIRS data we have. So in order to do that, we design an experiment. We ask subjects to inhale and exhale at a constant pace and a specific rate while sitting on a chair. So if you want to see the details about the work, you can just read our papers. So based on what I'm showing you, we ask subjects to breathe based on 6, 9, 12, 18, and 24 breaths per minute for each 50 seconds. And we recruited 20 subjects with different systems we had. So here you can see the result of the respiration rate as a function of the time. So the blue line is the reference respiratory rate, which was we recorded respiratory signals. At the same time, we estimate respiratory rate based on intensity modulation, amplitude modulation, and frequency modulation of the fNIRS data. So as you can see, within time, we really don't have that much of a difference between estimated and reference respiratory values for all of the modulation. So here, for this specific example, the mean absolute error between reference respiratory rate and estimated respiratory rate was lower than 0.71 breath per minute. Okay, so let's go to conclusion and finish our talk. So first of all, it's correct that physiological noise are annoying for us when we're going to deal with HRF. But their presence provide valuable opportunities for us to first use them for data quality assessment, which is really important for lots of research. That's really difficult if you have a really long data recorded, for example, for half an hour. Well, it's really difficult to manually assess the data. So thanks to existence of a cardiac pulsation on our algorithm, you can automatically do that without wasting your time. And secondly, those physiological parameters also, they provide us another chance to extract extra physiological measurements. Just imagine you have one sensor, for example, for recording fNIRS data, and you have three measurements. You have brain activation, you have respiratory rate, and you have heart rate. So you don't need extra sensors for that. You just have one sensor, but three physiological parameters. So as I showed you, it is quite possible to accurately estimate HR and RR from fNIRS. However, you should have this in your mind that the sampling rate is very important here. So in order to get a good estimation, you need to have at least sampling rate of 50 Hertz. So this is a very important criteria that we've been dealing with since last 2 years. And higher sampling rate even is better for us, because for the estimation we're doing for the feature extraction or modulation analysis we're doing, for example, respiration or for heart rate, sampling rate really matters. We're going to have way more clear data. And well, good news, if you're our customer, we are finalizing the testing of algorithms right now, and hopefully soon they're going to be implemented in our software so you can use them.